friends, let us talk about the QRA application problems in lecture 13. Where we are going to talk about, let us say, some application issues in quantitative risk assessments in module 3, where we are focusing on accident modeling, risk assessment and management. We already said in the last lectures that how one can handle different kinds of release scenarios like fire and explosion models. We have also said what will be the consequences in case of fire or explosion in terms of detonation, deflagration, etc. We have also said how overpressure and negative pressure can create damage on an existing system because of explosion. We also said how one can find equivalency of explosion damages using TNT equivalence. We are given equations to estimate them, and we also said what would be the over exposure risk limit in a given system for fire and explosion accident models. Subsequently followed by this, we also discussed about toxic chemical release models, where we said that chemical exposure index will be one interesting domain by which we can easily estimate the consequences indirectly. It has got certain prerequisites to do chemical exposure index. It also has certain advantages, and of course, it has got certainly a few limitations, but of course, globally the Dow CEI is acceptable as one of the powerful tools for estimating the damages which are envisaged because of probable or possible chemical releases in a given process system. Having said this, interestingly, there are many, let us say, application issues when you talk about quantitative risk assessment. We already said risk analysis can be defined as a systematic identification. Let us get back to the original definition of risk analysis. Is defined as a systematic identification and description of risk. It is very interesting. You have got to identify the presence of risk, you have got to describe what would be the risk. For example, identifying does not mean it will become a risk actually. You have got to describe the risk in terms of personnel, property, environment. So, it is a very broad term of risk analysis. In property, one can also include equipments, one can say asset. Therefore, QRA, which is quantified risk assessment, quantitative risk assessment, therefore, need to be focused on the identification of applicable hazards, description of hazards, of personnel, environment and equipment. Therefore, the analytical tools, analytical methods of risk assessment include identifying the presence of hazards and then assessing risk from the identified hazards. So, if you look at the flow chart of risk assessment, the first step obviously should be the system definition, then identifying the environmental conditions, then identifying the possible hazards, then from the possible hazards realization of them in terms of assessing risk. While doing so, one need to identify the initiation or initiating events, causes and consequences. So, these are important parameters, let us say gauge marks in QRA. As we now agree, in risk assessment the foremost step is to identify the hazard after you describe the system. Okay? After you describe the system, you identify the hazard first. So, what we call as hazard identification, which we already seen in earlier lectures. Let us quickly revisit this again and understand. Okay? Hazard. Hazard is useful in identifying the initiating events, it is done through a broad review of possible hazards present in the system, and also identifying the sources of accidents. So, most of the job of QRA is done at hazard stage itself. Then in that case it will lead to identifying the critical hazards and then classifying them. Based on the severity of consequences. What is the advantage of classifying them? Once you classify them, you will know what should be the decision on level of analysis. Some of the hazard identification tools can be listed. Some of the hazard tools could be checklist, accident and failure statistics, summary of near miss events, HAZOP, comparison of studies in terms of severity of consequences, which can be then applied to project level, system level, segment level, equipment level. If you recollect, interestingly FMEA could be a useful tool in equipment level. If you recollect, interestingly HAZOP could be a useful tool. If you recollect, interestingly HAZID or what if, etc., could be a useful tool. So, at different levels we keep on doing them, in fact even operation level, all. Okay. As we agree and understand now that hazard identification is more or less leading to the summary of causes and consequences. To take it forward to QRA, instead of doing hazard analysis, one can also do cause consequence analysis. So, let us talk about cause analysis. Cause analysis identifies the causes alone that may lead to initiating events. It assesses the probability of such events. Such events means the initiating events. We all agree that it is important to identify the cause of hazards or initiating events, because they will be actually the starting point of potential accident sequence. So, initiating events are starting point of potential accident sequence. I mean, it starts from there. It is very, very important statement. So, cause analysis helps us to actually identify these initiating events. Identifying the initiating events is done through a qualitative approach. Initiating events are identified through qualitative approach. If we really wanted to find the probability of initiating events, then this is done through quantitative approach. Identification is through qualitative, probability of occurrence of the initiating event is through quantitative approach. The qualitative analysis identifies the causes, the qualitative analysis identifies the causes that lead to initiating events, it also identifies the possible combinations that may result in occurrence of incident. Some of the qualitative analysis could be examples which we already studied, but still examples could be HAZOP, preliminary hazard analysis, failure mode effect analysis, failure mode effect criticality analysis, human error analysis. It is very interesting, which will try to tell us what could be the probable oversight which essentially come from near miss events or reporting of near miss events. You will be able to get human error analysis. One can also look at task analysis, one also look at error mode analysis. If you look at alternatively the quantitative approach, which will lead to estimating probability of occurrence of initiating events, some of the examples could be fault tree analysis, event tree analysis, synthesis models, Monte Carlo simulation, and one can also use Bora methodology. Interestingly, all are elaborately explained in Srinivasan Chandrasekharan 2016, risk and reliability of offshore structures, which is CRC plus. The reference in terms of ISBN number is available in the reference section of NPTEL website of this course. Parallelly, we also have one more course on NPTEL which talks about risk and reliability. Please look into this course. Very brief examples and very interesting definitions of these kind of assessment are also explained in this course. So, for parallel understanding and additional reading, I would urge that you can go through these lecture notes from NPTEL, which is again free, plus the reference to this textbook which has been authored by me. Now, let us talk about fault tree analysis, which is one of the quantitative risk assessment methods which are useful in identifying the probability of initiating events which can lead to incidents. Fault tree analysis links the final event with the basic event, It does it through a sequence of intermediate events. This uses deductive logic which means that it progresses backwards starting from the final event. Let us say for example, the final event may be for example is fire or explosion. Then for that particular event, which is the final event, final, intermediate and initiating events are identified which are consequently interlinked through different gates. Let us say the basic event is indicated in this manner, the intermediate event is indicated in this manner, and the undeveloped event is indicated in this manner. These events are generally connected through logical gates. There are two kinds of gates. This is what we call as AND gate this is what we call as OR gate. You can use both the gates in the logical analysis in building a fault tree to really connect these events. So, therefore, the probability of final event is calculated or is computed using AND gate and OR gates. Let us take an example quickly. We need to construct a fault tree for the formation of fireball. Let us say the final event which we identified is the fireball. When this can occur? When the chances of liquid petroleum gas is released from a pressurized vessel then this can occur. The reasons are the chances or the reasons. of release of this particular gas could be weld failure, can also be opening of relief valve by the operator, by mistake, etc. So, one can look into the detailed possible causes in a chemical manner of occurrence of fireball from the LPG gas release, looking at David and John 2007, Marco Pontiggi et al. 2011. For more understanding of chemical phenomena of formation of fireball from that of LPG release from a contained pressurized vessel. Because of the chances or reasons of weld failure or opening of relief valve when the LPG gas released from a pressurized vessel, which could result in a fireball as a final event, the flammable mixture which is formed now will get ignited if there is an ignition source. Once it is ignited, it becomes a fireball. So, all these events put together can be demonstrated easily using a fault tree analysis. So, please pay attention to the figure shown on the screen now. Let us say the final event is the fireball working backwards. We have different kinds of gates, as you see in green and blue color, different kinds of gates, AND gate and OR gate. So, the reasons could be to estimate the probability of failure of a fireball. We could have an LPG release and ignition source both present, then only one can have a fireball. LPG release can occur either due to weld failure or due to relief valve failure. So, the probability of weld failure in a given system is, let us say, P1, and the probability of relief valve failure in a given system which can lead to LPG release could be P2. So, LPG release can have a possibility of P1 plus P2 as a failure probability. Similarly, ignition source can be either from a cigarette or a smoking zone or from a friction spark, which can also occur from a mechanical aberrations of different systems or moving of cranes, objects, etc. So, the probability of each one of them is taken as P3 and P4. Ultimately, one is interested to know what is the probability of occurrence of fireball provided the LPG release probabilities and the ignition source probabilities of the system are known to me. Let us say probability of LPG release is P1 plus P2, probability of ignition is P3 plus P4, and one can say the probability of fireball occurrence is the probability of LPG release multiplied by the probability of ignition source. I can easily get the probability of fireball with a simple example demonstrated here. The next study, which is also interesting, which is an event tree analysis. Event tree analysis is an inducive approach. Whereas fault tree was deducive approach. It progresses forward whereas fault tree was progressing backward. It progresses through subsequent events leading to the consequences. One can also illustrate ETA through an example of a leakage of LPG from a load tanker. Let us say there is a road tanker, LPG gas leakage takes place from the road tanker let us say the probability of encountering an ignition source, let us say probability of ignition source is let us say 0.45, which is assumed. Basically, it is assumed based on inspection and experience. A fire, if formed, could transmit to an explosion. Okay. Fire, if formed, could become an explosion. Let us say that probability of becoming an explosion is only 0.2. So, let us construct the event tree for this. Please pay attention to the event tree constructed and shown on the screen now. Let us say LPG leak is what we are looking at. There can be a possibility of no ignition source and ignition source. In case of no ignition source, it cannot lead to explosion. In that case, then the issues are explosion and dispersion, which can be 0.95 and 0.05 if there is a possibility of ignition. In case of ignition present, then in that case fire without explosion can be 0.8 and 0.2, because explosion is 0.2 and without explosion is 0.8. So, one can lead to fire in case that explosion is for certain. One may not have fire, fire without explosion. So, one can have fire with explosion, one can have fire without explosion. So, one can easily find out the arrangement of events in different formats, lay them connected and try to find out what is the probability of the end product, which is nothing but fire with explosion or fire without explosion. The initiating event could be a road tanker leakage. It means this progresses forward from the event identified and takes it to identify the probability of failure of the consequence, whereas in earlier case it started from the end event and progressed backwards. Okay, that is the difference. When you look at QRA methods in general, there are many disadvantages. Let us see what are the disadvantages. Different approaches in QRA give different results. So, it depends upon what to be trusted. Scenario selection is very important, as just now we saw in the last lecture. Scenario selection is very important to have an accurate result, and it depends on expertise of the risk assessor. Changes in environmental condition also play a very important role in risk assessment in QRA. For example, temperature, wind, both velocity and direction, rainfall, relative humidity, day or night, etc. Each software which are used for simulating the model used for simulating for failure models may give different results for the same scenario. So, it all depends upon how do you handle the uncertainty in the software or in the failure models. Interestingly, all countries do not have statutes specifying acceptable risk levels. Statutes specifying acceptable risk levels. So, database used for estimating the probability of failure of any specific event makes a very significant difference in the result. So, as we said, when you talk about assessment, then you should say what is acceptance. So, if you look at the risk acceptance criteria, which is very important to compare the calculated risk from QRA study of the plant with that of the acceptable limits. Different countries follow different acceptable standards and criteria for process industries. Interestingly, I will show you a brief summary of the table. Please pay attention to the risk criteria in various countries as compiled by IS 156 2006. Look at the authority and application, VROM, the new one, the proposed one, and the existing one, HSE UK and HSE UK exclusively for nuclear power stations and nuclear industries. The maximum tolerable risk per year is changed depending upon the standards what the country follow. The negligible risk or the risk identified as negligible per year is also identified here. So, one may ask me a question, how these two numbers are different for me in defining risk acceptance criteria. To talk about risk acceptance criteria, let us talk about then the risk acceptance triangle, what we call Allard triangle. One can see here in Allard triangle as shown in the screen now, it contains three regions. The bottom one is what we call broadly acceptable region where the risk is highly negligible. The top one is called unacceptable region where the risk cannot be justified at all. The middle region is the Allard or tolerable region where tolerable only if further risk reduction is impractical or the cost is not proportionate to the benefit gained. So, friends, it is very important to fix up these boundaries. Okay. So, these boundaries are nothing but the values what you see in the screen here, which are given by maximum tolerable risk and negligible risk. Let us see this particular content in the screen back here. This is going to be my boundary for maximum tolerable risk beyond which the risk becomes unacceptable. This is going to be a boundary below which the risk is negligible. So, this boundary lines are given by different standards of international agencies which are followed by different countries. So, this region is the acceptable or tolerable region what we call as Allard, where Allard stands for as low as reasonably practical. So, you have got 3 regions. This is acceptable, this is negligible, this is unacceptable, and this is tolerable. Let us put it as tolerable. So, this boundary and this boundary which fixes my tolerable region or acceptable risk region is what we call as ALARP region, which is defined by different countries by different international standards, as you saw in the table just then. Therefore, friends, the line which divides the risk into broadly acceptable and broadly tolerable or broadly unacceptable varies from different standards and practices in different countries. Therefore, one cannot really quantify risk in sense whether the risk is really acceptable or tolerable, depending upon what kind of practice you are following. Okay? And interestingly, many countries even do not have the standards to be followed. Therefore, they follow or adopt international standards of different countries. Therefore, there is again a big guess, a big anomaly in fixing these borders of acceptable region or tolerable region of risk. Of course, let us please agree and understand, for an offshore industry, the statutes of international regulations prefix these values. One cannot keep on changing these limits as and when the industry is being formulated. These standards are prefixed. Okay? However, on what basis they are prefixed? Can they be altered? Can they be revisited? It all depends upon the country's statutes or what practices do they follow in respective countries. The maximum acceptable risk in offshore process industry downstream sector is 1 into 10 power minus 4 per year. That is the maximum limit. Above this value risk becomes unacceptable. Therefore, in between is the ALARP region, which shows that risk is tolerable only if further risk reduction becomes either impractical or the cost involved in risk reduction is not proportionate to the benefit gained because of risk reduction. Okay? That is the ALARP triangle. So, friends, in this lecture we understood about the application issues on QRA. We have also understood what are the important data required to do qualitative and quantitative risk assessment methods. We have seen some examples. We have also understood how to construct a fault tree and event tree in simple form for identifying a specific fault or a specific probability of failure in a given system. And we also seen in the summary at the end what are those issues which makes actually risk manageable or acceptable, provided you estimated risk using QRA techniques. However, whatever estimate you make from QRA techniques, which has got certain uncertainties, certain difficulties in terms of methods by which you are employing and country what you are following or practices what you follow, the acceptability of risk what you deduce from the models is depend upon what is the statutes you are adopting or what practices you are following in your country. So, it is very interesting that we do not have a global single standard of acceptance of risk which can be applied to all countries and all process industries, because it is all depend upon the economic index of a specific country, the process of style of manufacturing and the product cost, the taxes, the public interest, etc. So, therefore, there is a very large embrace to understand risk definition in terms of global standards, but certainly we have to agree that standards have been formulated and industries are following them stringently, so that we are all the time aiming to manage and reduce risk, and we have to agree at a final statement that offshore industry in terms of process industry is not a zero risk industry. Because of high degree of uncertainties involved in the whole process, you cannot actually make risk as practically 0. You design them to become 0, but however because of environmental conditions, because of operational variations, risk will be envisaged and risk will be present. So, what we have got to look at is the risk available or projected or probably identified is within the acceptable limits or not. If not, we should manage the risk, so that bring it to the acceptable level. If it is already in the acceptable level, let us try to maintain that level, so that does not go to an unacceptable standards. Okay? Thank you very much.